So, as a subject or a discipline of science, physics is mostly concerned with motion and that's movement. It's concerned with forces, that's pushing and pulling. It's concerned with heat, and energy. Physicists study electricity. They also study optics or light. And if you're studying astronomy, that's also, falls under the physics umbrella of science. So physics is quite a lot of things. But in Year 6 science, we'll be mainly focusing on electricity and energy. Now, electricity is actually something, it's basically the flow of electric charge. And it really means normally the flow of these teeny tiny things called electrons. So whenever electrons are flowing, you've got electricity. And that's what we'll be learning a bit about at the moment. Importantly, whenever you're studying electricity, you need to know a little bit about something called an electric circuit. So I've got a picture of an electric circuit here, and most electric circuits are made up of at least 3 things. And I've got a picture of them all right here. So electric circuits always have something called a power supply. So in my electric circuit here, the power supply is a battery. But the power supply could be, a coal-fired electricity generator. The power supply can be coming into your house as electricity. The power supply could be a solar panel. Could be lots of things, but in this circuit, the power supply is a battery. Electric circuits always have something called a load. So a load is the thing that the battery powers. So in my example here, my load is actually a teeny tiny light globe. So the battery in my electric circuit powers the light globe. So we've got a power supply and we've got a load, and something else which most electric circuits certainly have is something called a switch. So this here is a picture of a switch, and the switch can either be open or closed, and that either allows electricity to flow or it doesn't allow electricity to flow. I want to expand on that a bit more in terms of electricity flowing, because something that's really, really important when you're learning about electric circuits is that the circuit has to allow electricity to flow, or electrons to flow all the way around the circuit. So in this example here, I've got a battery, an electric charge, or electrons come out of this battery and they travel along this wire. And they travel along the metal part of the switch here until they get to this point right here. Then if this switch is open, so if there's a gap between these 2 little bits of metal here, then electricity won't be able to flow up to the top of the switch, and electricity won't flow around the circuit, and the light globe won't turn on. But if I close this switch, so if I in fact push down on this switch, then electricity will be able to flow. So there's 2 bits of metal will touch, the switch will be closed, electricity will flow, it'll flow all the way along this bit of metal, it'll flow along this connecting wire, it'll flow into this light globe, and that'll be great because then the light globe will shine up. But importantly, electricity will continue to flow along the circuit to the other end of the battery, and then the battery will continue to push electrons or electric charge out, and electrons or electric charge will continue to flow around the circuit and keep the light globe glowing. But as soon as we open this switch, so as soon as we stop the flow of electricity, the light globe will turn off. So having a complete electric circuit, often closed by a switch, is something which is really, really important. Now, while we've got this picture of this electric circuit here, I'd also like to talk a little bit about how scientists communicate information about electricity or electric circuits. So if I was a scientist in one part of the world and I wanted to tell another scientist about my electric circuit, well, I could try and draw this picture here of the battery and the switch and the light globe and all these wires, but it'd be pretty hard to draw that picture. So instead, what physicists do when they're explaining electricity is they draw circuits in terms of their symbols. So there's a few different symbols with electricity. But if I was going to draw this circuit, what I would do is I'd draw a picture of a battery or a symbol for a battery. And the symbol for the battery is 2 lines like this, one tall line and one short line next to it. So that's part of this circuit. I have a battery. Something else that I would draw on this circuit is, I would try and make my lines pretty straight. I'd also draw a symbol for a light globe, and that, a circle with a little semicircle inside it, that's the symbol for a light globe. Something else this circuit has is it has a switch, and this is a picture of an open switch, or a symbol for an open switch. So what I've drawn here in symbols is this electric circuit here. So just to, to show you which part is which, this here, this part of my circuit diagram is a switch. This part of my circuit diagram is a battery. And this part of my circuit diagram, this is the symbol for a light globe. So when scientists draw electric circuits, they actually don't draw them in terms of pictures, they draw them in terms of these funny little symbol diagrams. So that's all sorts of information about electric circuits. Now, a great use of electricity is, of course, to make light. And we've probably all got lights all over our house, and electricity powers light. So I just want to quickly run through how old-fashioned light globes work, and I'll tell you maybe a little bit about new-fashioned light globes. But what I've got here is I've got a picture of a light globe, and I'll tell you what happens to make light. So basically what happens is electricity flows from the main power supply, so that would be down here somewhere. It flows up through these wires up to here, and then it flows along this little bit of metal here. It's kind of a bit bright. That's actually called a filament. And the filaments of light globes is what makes them bright. And the filaments are often made of a special metal called tungsten. So the electricity flows up this wire, it flows along the filament, and then down this wire back to the electric circuit, and then the circuit would be completed. So electricity can flow all the way around this circuit. There'd probably be a switch here somewhere, but the filament is really the key part of the light globe. So what happens here is when electricity flows along this filament here, the filament gets really, really red hot, and it gets so red hot that it actually emits light. So all light globes do is they heat up a bit of metal until it gets red hot or white hot, and then that white hot metal emits light. And that's really all old-fashioned light globes are, a really hot piece of metal which emits light. Now, unfortunately, old-fashioned light globes aren't really very efficient because lots of the electricity is converted into heat. So if you've ever touched an old light globe, you'll find that they're emitting light, but they also get really, really hot. So they're not super duper efficient, but they are really, really good at creating light. New light globes, like fluorescent light globes, electricity runs them still, but in fact what happens is the electrical energy powers a gas, or gives its energy to a gas inside the fluorescent light, and then that gas itself basically emits a light, and that's how fluorescent light globes work. So it's not a piece of metal getting hot and shining a light. In fluorescent light globes, it's a gas which basically absorbs the electrical energy and emits a light energy. So old-fashioned light globes aren't as energy efficient as new fluorescent light globes, but they still do a pretty good job at making light. So something which comes up when we're discussing circuits is different types of circuits. And there are two main types of circuits, electrical circuits. They are series and parallel circuits. And I've got a picture of a series circuit and a parallel circuit here. So this here is a series circuit and parallel. This is a parallel circuit. So there are two different types of circuits. You can see they're quite similar in that both of these circuits have got two light globes. 1, 2. They've both got a battery, and they've both got a switch as well. So they've all got the same kind of components in them, but they're arranged a little bit differently. So in a series circuit, all of the loads, or if they're globes, all of the light globes are connected in a series, so in a line, all together. So these are all in a straight line with each other. Whereas in a parallel circuit, the light globes are connected, parallel to each other. So one above the other, joined up by wires. And again here, so they're connected in parallel, one on top of the other. So something that's different about series and parallel circuits is basically the way that they make the globes work. So in a series circuit, all of the globes in a series they all share the power of the battery, I suppose. So the more light globes I add to a series circuit, the less and less bright all of the globes become altogether. Whereas in a parallel circuit, all of the light globes shine with equal and brightest brightness. So the battery gives its full power, I suppose, to all the light globes. So I could have 10 light globes in a parallel circuit and they'd all be just as bright as if I had one light globe. Whereas if I had 10 light globes in a series circuit, all of the globes would glow at about 1/10 of the brightness as if I had just one globe in a series circuit. So in series circuit, the globes will glow less bright. In parallel, they'll all glow as bright as they can. So, that's a pros and cons thing. Something else about series and parallel circuits is, if I have a switch in this series circuit and I close this switch, so I close this switch here, then all the light globes will glow and they'll all be on. But if I open the switch and I have a gap here, so electricity can't flow, so there's a gap here, then all of the light globes will turn off. So I can either have all of the light globes on or all of the light globes off, but nothing really in between. On this parallel circuit here, the way it's set up at the moment, if I turn this switch on, both light globes will turn on. So electricity will run around here and continue to go around the circuit. If I open the switch, so electricity stops flowing, then neither of the light globes will go on. But something that's really important here, if I instead put a different switch here, and I put a different switch here, what I could do is, if this switch was closed, or not even there, sometimes I could close this switch and turn this light globe on. Sometimes I could close both switches and have both light globes on. Sometimes I could just close this switch and have that light globe on, and sometimes I could have this switch open and have that light globe off. So in a series circuit, all the globes have to be on or off, and in a parallel circuit, you can have some of the globes on and some of them off at different times. So in fact, what you'll find is that in your house, you can turn some globes on and some globes off, and all the globes are always glowing at equal brightness. And that's because in your house, all of your light globes are connected in parallel, not in series. So there's different ways to connect circuits, connect electrical circuits, and you'll find that in your house, all of your light globes, and in fact all of the electrical appliances in your house, are connected in parallel. Now, when we're talking about electricity, something that comes up is two words. One word is conductor, and the other word is insulator. Basically, some materials are able to conduct electricity, and some materials are not able to conduct electricity. So conductors are things that can conduct electricity, and a good example of a conductor is some metal. So this is some copper wire. And copper can conduct electricity, which means free electrons or electric charge can move along the copper. Other things cannot conduct electricity, which means electricity can't flow through them. And an example of an insulator, a great example, is this plastic wire. So insulators can't conduct electricity, conductors can conduct electricity. And the reason why we have both conductors and insulators in our wires is basically so electricity doesn't escape. So all of the wires in your house, you'll see that they've got, you'll just see basically a plastic outer coating on all of the wires in your house. And that's so that basically when you touch one of the electrical wires in your house, you're not touching the conducting metal, because if you did touch the metal and electricity was flowing through it, you'd get a really, really nasty electric shock. So that's all about conductors and insulators. So when we're talking about electricity, something that comes up is energy. And there are lots of different ways to generate energy. One great way to generate energy is something called geothermal energy. And geothermal energy uses the heat of the earth, and it ends up using the heat of the earth to make steam, and that steam turns a turbine. So we'll go through that very quickly. Basically, in a geothermal energy plant, there's a pump, and this pump pumps water, cold water, down into the ground. And down deep in the earth, if you go deep enough down to the ground, it's really hot. And in fact, if you go right into the middle of the earth, it's, you know, boiling, boiling, boiling hot. It's really, really hot. But if you dig down quite a bit, it'll get to hot enough basically that you can turn water into steam. So we pump water down into the earth where there's this geothermal energy. So geo means, you know, from the earth really, and thermal means heat. So there's this heat down in the earth that turns the water to steam. The steam then travels back up to the surface of the earth, and the steam is pushed through a turbine. So that turbine spins around, and then that spinning turbine generates electricity and puts electricity into our mains power. So it's quite possible for there to be a geothermal energy plant which is delivering energy to your house right now. So, but basically, geothermal energy works by water being pumped down into the ground, it turned to steam, steam coming back up to Earth, turning a turbine which makes electricity. So that's how geothermal energy works. Another way to generate electricity is something called hydroelectricity. And once again, this uses a turbine to generate electricity. And we'll quickly run through how that works. So basically, you put in a dam. You put in a really big dam in the middle of a river or something, and what happens is on one side of the dam, you end up with a really big lake. So you end up with a big lake, and then there's an intake down in the dam here that allows however much water you want really to flow down this tunnel here. And when it flows down, it creates a bit of speed, and the flowing water spins again, so spins this turbine. And when the water spins the turbine, it basically powers a generator, and that electricity generator then spits out electricity, and the electricity goes to houses or wherever the electricity is used. So hydroelectricity, or you know, hydro means water, so water generated electricity is made by shooting water down to a turbine to spin the turbine to power a generator to make electricity. And then of course all the extra water just goes back into the river, and it's a really great way to make electricity, hydroelectricity. Another super duper way to make electricity, or to, you know, convert one type of energy into a different type of energy, is solar power. So solar power is great because the sun provides Earth with heaps and heaps of energy. So basically, solar power works by something called the photoelectric effect. So photo means light, electric is electricity, and you know, an effect is some sort of effect. So the photoelectric effect is basically a process where light is converted into electricity. And electricity is the flow of electrons. So what happens in the photoelectric effect, very briefly, is sunlight hits a material which is photoelectric, which is capable of turning light into electricity. This special material then basically absorbs the light, and it generates little electrons, so that's electricity. Light hits these photoelectric material, it generates electricity, or electrons. Those electrons flow down these wires, and they turn on a light globe. So that's really quickly how solar power works. So there's special materials which can be photoelectric, which means they have the capacity to basically, when they're hit with sunlight, to eject electrons, shoot off electrons, and those electrons, any flow of electrons is an electric current, and that's electricity. So solar panels are made of these photoelectric materials, and that's how solar power works. So this is one solar cell here, and that's obviously not going to provide a great deal of electricity. But if we want lots of electricity, what we can do is we can get one solar cell and join it together with a bunch of other solar cells into a module. And then if we want even more electricity, we can get a bunch of solar modules and join them together into a solar array. And then we can get these enormous arrays and put them, maybe in the desert. And all of those solar cells in arrays, in giant arrays, they'll generate heaps of electricity because of something called the photoelectric effect. And that's, basically where some materials absorb light and release electrons. And that's how solar power works. So I've already been explaining quite a lot about energy, and you might have picked up that there are different types of energy. So there are two main types of energy. So there is non-renewable energy, and that's actually where most of our energy comes from at the moment. So this is things like burning fossil fuels. So burning oil, burning coal, and burning natural gas, and we dig fossil fuels out of the ground. So they're non-renewable basically because they're going to run out. If we dig into the ground, there's not an unlimited supply of coal. At some stage, coal will run out and we won't be able to burn it anymore to make energy. So that's why it's called non-renewable. So non-renewable energy is basically, it's not sustainable and it's energy that will run out eventually. So the other type of energy is renewable energy, and this is basically energy that will never ever run out, or it won't run out for billions and billions of years. And there are a few great examples of renewable energy, and renewable energy is a really sustainable way to use energy. So there's solar energy, and the sun's up in the sky, it's not going anywhere, it's going to be there for billions and billions of years. So getting energy from the sun is a great way for us to use energy. Another way is geothermal energy. So we talked about it earlier. So geothermal energy is getting our energy from the heat within the earth. So there's lots of heat in the earth, and the earth will, again, for billions of years be hot on its inside. So we can use that energy and it will never go away. So it's really sustainable. Hydropower energy. So this is, using dams to collect water to turn turbines. Water's not going away on planet Earth, so that's also a super duper way to generate electricity, is to convert hydropower into electricity. And wind energy. So the Earth will always be windy, so if we have some wind farms, that's another really good renewable way to generate energy, because wind will always be there and it won't run out. So there are these two ways you can generate energy. One of them is non-renewable. It's not sustainable. We won't be able to use that forever. We really do need to start using more renewable or more sustainable ways to generate energy. And that's things like solar power and geothermal energy and wind energy. So they're the two main types of ways to generate energy.